Right, hello, welcome to another video. This is a question from an A-level maths paper from a couple of years ago. I found it to be quite an enjoyable question to do in relaxed conditions. I imagine as an A-level student in exam conditions it would probably be quite a stressful thing to have a go at. But we're going to have a go at it now, and I've had a lot of fun doing it. Hopefully you'll have a lot of fun watching it and kind of going through the steps. So it's question 16c. I did put that in the 16c says a sketch of the graph of y equals e to the minus x sine x for x being equal to or greater than 0 is shown below. The area of the finite regions bounded by the curve and the x-axis are denoted by a1, a2, so on and so forth, all the way to an. Then it says find the exact value of a1. I took this to mean integration questions. So firstly, we have our function here, and we need to find an area underneath a curve. So we need to integrate this function in between two bounds, and that's what we're going to do. So firstly, we need to work out what our bounds are. Well, our first bound is 0 because the question says for x being equal to or larger than 0. And then we need to work out what all of these points are where it crosses the line. Well, we can do this through just inference, because e to the minus x is if it was just e to the minus x, it would never cross 0. It would kind of tend towards 0, but it would never actually hit 0, because e to the 0 is 1, and when e to a power, when the power is negative, you get numbers in between 0 and e. But yeah, e to the minus infinity is essentially 0, but like I said, it never hits 0. So this only hits 0 because we have this sine x on the outside, and sine of 0 is 0. So, sorry about that. So we know that these 0 points are in relation to the sine x, not in relation to the e to the minus x. So if we draw a regular sine graph, we know it looks something like this, and that looks quite similar to what we have here, except the sizes in between the graphs are getting smaller until eventually we get very, very small. Over here it's very small in comparison to over here where it's much bigger. And then this kind of relies on you knowing your sine values. Sine of x is equals 0 for sine of x plus n pi, where n is a real number. So when you have like sine, actually I think I'd like to get rid of this and have it as this: sine of n pi. So sine of pi is sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, so on and so forth. Yep, I just thought I'd double check just on the safe side. But yeah, so sine of any whole number multiplied by pi will give you 0. So our first one, going in a positive direction from 0, is going to be 1 pi. So our top bound is pi and our bottom bound is 0. So now if we write down our function here, e to the minus x sine x. I'm just going to rub out this bottom bit here. There we go. And then what we can do here is carry on with integrating our function. I used integration by parts, which can be quite an awkward method to use, especially if you're trying to remember it and you're not given the formula for it. So I'm going to write the formula just down here, and this is how I've been made to remember it. The integral of u multiplied by the derivative of a function v equals uv minus the integral of the integral of v multiplied by du. So in our first part here, we leave u as it is, but we have to integrate our derivative of v to bring it back to v. Then we subtract another integral of v again, so we have to again integrate our du, and then we have to derive our u to make it du. So here we have to pick which part of the integral we actually want to differentiate and which part we want to integrate. At this point, it doesn't really matter. E to the minus x doesn't really change. The only thing that changes is the sign. Because we have e to the minus x, if you integrate it, it becomes minus e to the minus x. If you differentiate it, it becomes minus e to the minus x. It becomes the same thing whatever you do to it. Sin x goes through a cycle. If you differentiate it, you get cos x, then you get minus sin x, then you get minus cos x, then you get sin x again. And then if you integrate it, you get minus cos x, then you get minus sin x, then you get cos x, then you get sin x, and it's just a cycle. It doesn't really matter. If we had something like x squared e to the x, then you'd want to differentiate this x because eventually it would go down to nothing if you did it long enough. Whilst the e, you could just integrate it and it would never change. But yeah, so for this, it doesn't really matter. You will probably get, I think you get the same thing either way. I chose to, what did I choose to do? I chose to integrate the e function, the exponential function. So we're going to integrate our e to the x, which gives us minus e to the minus x. Our sin x doesn't do anything, so we leave it as it is. And for this kind of thing, I am going to, and you will see why I do this later, I'm going to call this integral a. And I'll come back to that in a bit, and you'll see why I've done that. It's quite a neat trick for doing integration. So if we carry on with our bit down here, we're going to subtract, we're going to do an integral sign, we're going to integrate our e again, so we get minus e to the minus x, and then we're going to differentiate our sign, and that just gives us cosine x. Now we can't leave this as it is because we have another thing to integrate, but what we can do is that we can bring our negative, because essentially this negative is just -1 multiplied by everything else in there, we can bring it out because it's just a constant, and we can turn this into a positive. So now we are just integrating e to the negative x cosine x. And let's do the same thing as before. We're going to integrate our exponential function and differentiate our trigonometric function. Let's do an x there just to avoid confusion. So minus e to the minus x again, multiplied by cosine x. I'm just going to make sure I'm recording. I'm recording, good. Oh, thank God. That would be very inconvenient if I wasn't recording this whole time. Minus, because we have to subtract before we do our integral, the integral of, again, we integrate our e to the minus x, so we have a minus e to the minus x. If we differentiate our cos, we get minus sine. I'm going to put a little dot there just so we know that we're multiplying these two and it's not two things being subtracted. Minus sine x. And because we have two negatives multiplied by each other, we can just make them both positive. And now we have the integral of e to the minus x sine x. I'm going to get rid of the little bit here. And this is why I called our original function a, because this here is exactly the same as this here. E to the minus x sine x, e to the minus x sine x. So what we can do, and this is quite cool, we're going to just get rid of everything here, and we're just going to call it a. A, there it is, a. So if we write down our original, in fact, let's not write it down as the original, let's just call it a. So when I write down a, you know exactly what I mean. So a, which is the integral of e to the minus x sine x from pi to 0, equals minus e to the minus x sine x plus minus e to the minus x. Oh, nope. Cosine x minus a. And now we can just solve for a. So if we bring our a's all onto one side, we get this equals 2a. And now we can just halve this, and we have our terms for a. So if I just do a little box just to separate it, a equals a half of, and what we can do here, we can just bring out e to the minus x as a common factor, sine x, and because we've already, in fact, I'm going to bring out the negative just so we can call this minus e to the minus x sine x a positive, sine x plus cos x. And this is the first part of this question done. So what I'm going to do is I'm going to erase all of this. So if you need to look at it, just pause the video. I'm going to erase this all now. So we have our term for a, which is the integral of what we're looking for. So it's minus a half e to the minus x sine x plus cos x. So now we want to put this in between. In fact, what we can do here is we can bring our minus half out as just a coefficient because it doesn't rely on x. E to the minus x sine x plus cos x between pi and 0. So let's start with pi. So minus a half, and let's just bring it in all between here. E to the minus pi sine of pi, which is 0, plus cosine of 0, which is 1. Is it 1 or is it minus 1? So I'm just going to double check this. I don't have to really use these. Cosine of 0 is 1. Yeah, I thought it was 1. Okay, so e to the minus pi 0 plus 1 minus e to the 0 e to the minus 0, which is e to the 0, which is 1. So we don't need to write an e to the minus anything here. Sine of 0, which is 0. Oh no, sorry, wait. What am I doing? This is basically the sine of pi. Sine of pi is minus 1. That's the mistake I was making. So I was wondering why this working out didn't match my working out that I've written down to the minus 1. Minus 0 plus 1, because cosine of 0 is 1. And this gives us minus a half. Open our brackets. Minus e pi minus 1. And when we just distribute the negative, we get half of e to the minus pi plus a half. Or if you want to leave that half out of the bracket, half e to the minus pi plus 1. And there you go, that's the first part of the question anyway. The second part of the question I found a little bit more difficult, but still I had a pretty fun time with it anyway. So like I say, if you need to pause it, just pause it. And here we go. Show that a to the 2 over a to the 1 equals e to the negative pi. So this time it wants us to find the area of the second bit. So it's this bit here that we're looking for now. So we found a to the 1, now we're going to find a to the 2. Now this bit is going to throw a little bit of a curveball at you, because it's looking for an area of the graph that is under the x-axis. So it's going to give you a negative number. It's going to give you a negative area because in comparison to the x-axis it is negative. Don't let that fool you. Areas can't be negative. Areas can only be measured in positive numbers. So when you get that negative, it's gonna throw you because you think, oh my god, what have I done wrong? And you're gonna go look back through you. Because this is what I did, because I haven't done a question like this in a while. You're gonna look back through your working and think, oh god, what have I done? My number's negative. No, that's fine. You just explain that areas can't be negative, therefore it is a positive, and you just change the sign to make it a positive number. So yeah, let's actually get to the question and I will show you what I mean. So a to the 2 equals, and now we've already done our integration. We've already found what the general integration term is, and that is this here. So we can just take this, but just this time change the balance. So minus a half again, e to the minus x of sine x plus cos x. But this time we're going to go from 2 pi to 1 pi, because as I explained earlier, these points where it crosses the x-axis are all multiples of pi, and eventually it will just go to pi n sine. There we go, something like that. So anyway, so we got 2 pi to the negative pi. So now if we do our plugging in of numbers, we go e to the negative 2 pi. Sine of 2 pi is 0. Cosine of 2 pi is 1. So we have our positive 1 here, minus e to the negative pi. And then in our brackets, we want sine of pi, which is 0, cosine of pi, which is minus 1, and this gives us minus a half of e to the minus 2 pi minus minus e to the minus pi, but because our bracket has a negative 1 in it, we can just make this a positive e to the pi. We can bring out e to the pi as a common factor, so now we are just left with e to the negative pi, and then what we've got left in here is e to the minus pi plus 1, because e to the minus pi times e to the minus pi is e to the minus 2 pi. As you should know, when you multiply powers, you just add them together. Minus pi is minus 2 pi. But it doesn't want us to just stop here, it wants us to show that a to the 2 over a to the 1 is e to the negative pi. So, oh, and I forgot, yeah, this is it originally is a negative, and you're going to think, oh, no, I've done it wrong. Nope, you just have to write something along the lines of areas cannot be negative, and then just make it positive. That you can just do that. That's just the thing. So a to the 2, if we do our big fraction, we have half e to the minus pi, brackets e to the minus pi plus 1. If we go back to our last question, we can see that our answer is half e to the minus pi plus 1. Minus pi plus 1. And we can just cancel down some terms. So we cancel the... In fact, can I undo? No, I can't. I'll just leave it as that. Okay, so we can cancel the halves, and we can cancel the whole thing in the bracket. And this is why I wanted to bring out that negative pi from this here and result in this, because it helps us with cancelling. And what we're left with is just e to the negative pi. And that is our answer for the second part of 16C. Like I say, I found it a little bit difficult to begin with. Then again, that was just because I forgot that I did a bit of a panic when I found that my integration was negative. But you know, it's fine. I look at the mark scheme. I realise, oh, I'm being a bit daft. You know, you can't have a negative area, and because the that part of the graph is under the x-axis, it is going to come out as negative, but you can't have a negative area. You measure areas positively, so you just have it as a positive number. As long as you write something along those lines, you will get the mark and you'll be fine. So the last part says, given that a to the n plus 1 over a to the n equals e to the minus n, show that the exact value of the total area enclosed between the curve and the x-axis is 1 plus e pi over 2 brackets e pi minus 1. So, this bit wasn't too difficult, I didn't find. Well, it is difficult until you make a connection. And the connection is that we are looking at a geometric series. A geometric series is a series that can be expressed like so: a plus ar plus ar squared plus ar cubed, and so on all the way to ar to the n. Some final power. So this can be expressed altogether as a over 1 minus r. This is what it will tend to, as long as r is in between minus 1 and 1. And our r, which is given here, is e to the minus pi, and you can do this on your calculator. In fact, I'm going to just put it into Google now. Minus pi is 0.04321391826, and that's obviously in between minus 1 and 1. So we can use this summation to find what is in a geometric series. So we want our A. Our A is just our first term. Our first term is going to be this. Our A1. Our A1 equals A. Our A2 will be A R. And this is why the second part of the question wanted to show you that A1, A2 equals e to the minus pi, because that is the thing you multiply the last term by to get to the next term, and then so on and so forth. That is our R, because the difference between AR and AR squared is that we've multiplied by R. And then here we've multiplied by R, and so on and so forth. And yeah, that's why it's done that. So if we plug our numbers in, if we go back, our A1, which is half e to the minus pi plus 1. Oh, let me get the pen back up. So A is half e to the minus pi plus 1 over 1 minus R. R is e to the minus pi. So if we just get rid of our R, e to the minus pi, and we could leave it at this, but it doesn't want it expressed like this. It wants it expressed as it is in the question. 1 plus e pi over 2 brackets e pi minus 1. And you're probably thinking, well, what do I do here? You know, how do I get the minus pi to become a positive pi? And it's this is a little trick. Multiply the top and bottom by something, manipulate the fraction to look like something else, but equals exactly the same thing. And what we're going to do here, we're going to multiply the top and the bottom by e to the pi, e to the power of pi. Now when we put this into our bracket, e to the minus pi times e to the pi, well, if we add those together, minus pi plus pi is 0, e to the 0 is just 1. So our bracket as function has now become, our fraction, sorry, has now become 1 plus, now what is 1 times e to the power of pi? Well, it's just e to the power of pi. Now we go to our denominator. Again, 1 times e to the pi is e to the pi minus, and again, we just get 1 here. Now this looks a lot more like what we have in the question. We have our 1 plus e to the pi. We have our e to the pi minus 1. All we need to do now is bring this half out and just apply it to the whole thing instead of just the numerator. So when you have a fraction on the top of some fraction, we can bring it out and just multiply it to the numerator as so. So we can bring out the half. Because you're multiplying this whole thing by a half, you're just multiplying the denominator by 2. So we can just say that this equals 1 plus e to the pi over 2 bracket e to the pi minus 1. And there is our answer. This was worth 11 marks, I want to say. Yeah, 11 marks. So this question alone is worth a good chunk of your paper. So being prepared for these more difficult questions is something that can be really important. So that's me done, I'm afraid. That's the whole video finished. I'll try and find another fun little question for another video soon. Thank you very much. Goodbye.